Thanks, Jody, for setting me up for the talk. Hello, everyone. My name is Chin. I will tell a story today. It centers around simplifying the data management for a US DOE Premier Exascale Computing Preparation Project, LCIS-2, at the SLAC National Accelerator Laboratory. The story has been evolving since 2015. During this talk, I will share with you 5 key ideas reinforced with live demos. Any slide with a light bulb icon is an idea slide with a demo logo for demo. The first key idea is that a unified data mover simplifies data management. At a high level, from the viewpoint of IT, data management is the practice of collecting, moving, keeping, and using data securely, efficiently, and cost-effectively. Think about the definition a bit. You will see that all of them involve data movement. When massive amounts of data are involved, data management becomes extremely hard. By the way, the definition actually covers data curation, FAIR principle, and more. For example, data curation, the organization and equation of data, is covered by keeping. The FAIR principle is covered by using. In a modern distributed data-intensive organization, data management can be quite complex. So introducing different data movers only adds more complexity. For complex physics, a grand unified theory is the holy grail. For complex data management, a unified data mover is valuable similarly. Our current product ZX integrates 4 different products. Together, they offer simpler usage, consistent operation, and enhanced efficiency. The second key idea is that fast storage is the most critical to moving massive amounts of data, assuming there is enough network bandwidth and computing power. As far as the data mover is concerned, its parallelism and concurrency interacting with 3 other IT stacks are the most important aspects. A good metaphor is the large water transport system. Without sufficient water in the reservoir, even with large diameter pipes, plenty of electricity, and arrays of powerful pumps at both ends, generating good water flows is simply impossible. The third key idea is data movement categories. At the end of 2020, Dr. Les Cottrell and I published a DOE Technical Report, Data Movement Categories. We hold the view that knowing how to map a data movement task into one of the 4 categories helps select proper data mover tools. That's an important step in the creation of a unified data mover. Surprisingly, with many varieties of data movement, by staying at the high level, just 4 categories are enough. They are completely automated data movements, partially automated data movements and user-controlled, partially automated data movements but controlled by IT professionals, and strictly interactive data movements and user-oriented. Now, let's see how we can tackle the first 3 categories, the far more demanding ones than 4. Let's start from category 1. Our motivation for creating a data mover for this category is the Linear Coherent Light Source 2, also known as LCIS-2, the world's most powerful free electron laser, expected to be operational in 2022. We have been striving to meet its ambitious data movement requirements since 2015. These 4 are what we have faced. Bulk transfer, such as figuring out moving 20 petabytes of data over the 100 GPS ESNet in less than a month from Menlo Park to Berkeley in 2017. Enabling non-local collaborators to take their experiment results back home, but they don't run ZX. Oh yes, various storage management challenges such as migrating data from one raster file system to another, and finally, the append streaming, a very advanced and demanding form of streaming. From these 4, we really learn to focus on 3 product characteristics: simplicity, scalability, and efficiency. As a side, the volume of data generated by just a single week-long experiment takes more than 1.6 million man-days to create using a typical mobile phone. So what is append streaming? This is definitely not the common Netflix-style video streaming. It must handle multiple live, fast-growing files, which eventually can become very large, up to a few terabytes per file. Furthermore, the growth rate are really high, 100 gigabytes per second even after data reduction. That's 800 Gbps. Furthermore, data must be sent to both local and remote destinations at the same time. How to handle the difference in bandwidth, network latencies, and infrastructure reliability issues. Also, once the data reaches a supercomputing center, what is a good way to notify the tens of hundreds of analytical application instances running on the supercomputer? This part is still involving LCLS2 itself, but we have made some progress. As an example, to overcome the multiple destination challenge, we came up with a way called task forwarding. That is, data transfer tasks can happen in a chain-like manner. Why is this useful? Let me explain. ESNet Executive Director Inder Manga gave a feature talk on ESNet 6 in the DOE SE18 booth. I have borrowed a slide from his deck. As you can see, different segments of the ESNet 6 backbone could be of a different bandwidth. Around the Argonne National Labs Leadership Computing Facility, also known as LCF, the bandwidth is in general higher. So a possibility is for Slack to append stream data first to the nearby NERSC, then NERSC append streams to ANL LCF, which in turn append streams data to the ORNL LCF. This avoids having to do all three at the same time at the Slack. So instead of using a fork-like pattern, we use a chain-like pattern. Let me show you how this works. Task forwarding leverages ZX files side-to-side transfer capability. I will transfer from side A to side B first. Since I only have two nodes, so once side B has received the data, I will transfer it back to side A. Introduce some source file, this guy. Give it the name, give it the side B, enumerating file, sending, look at side B, transferring, highlight it, and let's watch the progress. So between the two nodes, we have 2 times 25 equals 50 Gbps, and the storage attainable throughput is somewhat higher than 50 Gbps. So under this circumstance, it's very easy for ZX to attain more than 80% of the network bandwidth. Okay. And as you can see here, so now done. Let's go back to side A. A original is the source side, so it has this related task. Okay, to avoid the conflict and makes A look like a fresh destination side, let me delete that task. So let's do that. Remove. Okay, gone. Now this is highlighted, so we just simply add it and say send to side A. And then come back to side A. Yep, see, it shows up. And the pickup should be very quick too. Let's watch. Yeah, you see, it's picking up. And the speed should be the same. Yeah, so around 22 seconds it should be done. It's 65%, 100% done. Okay, so let's close off this and get back to this and take a look at this slide again. So note that as you can see that ZX doesn't use a client-server model. It's a symmetric. Both instances can send, receive, even concurrently. Before going further, note that in this slide there are two sides A and B, right? What if the A and B collapse into one? In this case, a single instance of a ZX can get the job done. We call the single side mode, also known as SSM. It's actually very useful. Let's take a look at the category 2. Nowadays, owing to COVID-19, genome research has been actively carried out worldwide. This is a typical genome research lab. These boxes are so-called next-generation sequencers, also known as NGS. They consist of risking commodity servers, some running Microsoft Windows, some Linux. New models can spit out data around 20 terabytes per day. A large genome lab has many of them, so collecting data from them is a challenge. So far, at the smaller labs, usually data collection is handled in a very inefficient manner, often involving multiple expensive and complex NAS systems. Now let's simplify it. This slide shows how a single server can collect data from multiple biomedical instruments, then sweep the collect data automatically into central storage to be fed into processing pipelines. The exported NFS SMB shares look like a local subdirectories in the Linux server. The central storage is mounted in the server and looks like a subdirectories tool. So if a ZX can move data from a set of subdirectories to another, it gets a job done. This is done with a ZX SSM. Let's see how it works. And let's check this in the terminal. So this is the path. It has been mapped to a ZX input data path. We're using this data set, and this subdirectory is used as the destination. Right now it's empty. So we call up the web UI, browse 128, give it a name. This is good for ZX SSM local size file. Target. You remember this? Save. Okay. Enumerating. It should be starting copying, and it will ramp up pretty fast. In the host, the attainable storage throughput is slightly above 50 Gbps. With the ZX, it's very easy to attain more than 80% of that rate. Okay, so take a look. Yeah, see, it is. So by this rate, it should be done pretty soon. Let's see. Yeah, done. Double check in the shell. Yeah, got it. You can also look at that in the with the web UI tool. Under the files, you can even browse it. Let's move it aside and take a look at this slide again. Note that with this solution architecture, the left side is mapped to data movement category 2, the right side to category 1. Let's move to category 3. We'll use the file system migration as an example. If you need to migrate a few petabytes of data from IBM Spectrum Scale to BGFS, what do you do? Buying an expensive file system replication solution using rsync or PF2? No, let ZX SSM help you. You can do incremental replication too, which is important to migrating active file systems that are still in production. Let me show you how it works. And this demo shows ZX incremental replication. Let's review in this terminal first. You see the two data sets, snap0 and snap1. What are their differences? This JSON file actually defines how we derive the snap1 from snap0. So in this directory, some files are deleted. In DR0, one file is deleted. In DR1, two files are augmented. In DR2, and all the files are deleted. So this one should be gone after the replication, and the rest are just straightforward copies. And this subdirectory is used as a destination. Right now it's empty. Now let's use the ZX Web UI to do a single side mode migration, doing incremental updates. Let's see how it works. Browse 128, snap0, select all, give it the name. Snapshot is good, single side mode, so local side. Target, this one, you remember it. Save. So enumerating files, copying, and you know it's gonna be pretty quick. Okay, so let's just give it a little bit time. 12% now, 28%. Almost halfway down. More than halfway down, 61% now. 76%, getting close. 95. Done. So let's highlight it, update, browse, 128, snap1, select all, save. Look at this number, 128, but now it changed to 1.3 and it's finished. Why? Because the difference is really not that much, so it's quick. Okay, now let's check in the shell. See, DR2 is gone. Okay, so this is easy as 1, 2, 3. The category 3 is very large and important, but not widely known and visible. This is because usually only IT professionals are involved. But tasks in this category must be carried out in any data-intensive organization. tag refresh of a storage system is a common task that must be done periodically. The Zettar recommended approach is a simple 3-step process. 1. Get the histogram of the file size distribution, which significantly impacts the data movement rates. Do it like this. The X2X directory contains the typical camera output files in the media entertainment industry. 2. Run the Ubuntu storage suite to make an estimate how soon the job can be done. And to use it is really simple. Just do this. Okay. And I will show you a dry run too. So like this. The -V verbose mode shows you setup details. The -N triggers the dry run. A real run generates goodies like this. A graph, a GNU plot file in case you are comfortable using it, and a CSV file, and you can use a spreadsheet to do more plotting should you wish. Of course, textual output from Ubuntu for more details. All that generated hands-off. Very handy. 3. Use the ZX SSM to actually migrate data, that is, move, copy, and sync. And for multi-user data, you can preserve the file attributes if so desired, but let's do a bit review in the terminal again. In Linux, only the root user can do privileged operations such as a chown. So a simple way is to run ZX on the root. You can check like this. Please note that running any application on the root has really serious security implications, so try not to do it on a host that's exposed to the public network. There are several datasets. You can see directories and files owned by Alice, Bob, and Chris. And this is the intended destination directory, or mount point. Right now it's empty. Now let's use the ZX Web UI. Browse. Multi-user. Give it the name, call it MU. Single site mode, so local site. Now we click on the options. If we turn this on to basic, then ownership and the permissions are preserved. Target, of course, you want to select this. You remember this, right? Now, it starts copying. Give it a little bit time. The progress, as you have seen, it should be pretty quick. 10% already. 25. 40. Close to half. More than half already. 71%, getting close. 87. Done. So let's review in a terminal again. So getting to yes. So indeed, ownership and permissions are preserved. By the way, ZX preserves such attributes if so desired, regardless of its mode of operation, file, object storage. This dual InfiniBand-based setup is capable of migrating petabytes worth of data in days. If both the source and destination file system are fast enough, you can use a ZX cluster to boost the migration rate. IB bypasses kernel by default and is highly efficient, simpler to set up than Internet. It's a secure out-of-box, no firewalls needed. IB traffic is not IP traffic and is a layer 2. Easy cabling with up to 150 meters long active optical fiber for HDR and newer. it can migrate all kinds of file systems. The solution architecture can be used for even to facilitate migration. Often during such moves, migrating storage system is the most demanding. Back in 2015, ESNAP established a custom 400 Gbps connection called Bay Express to facilitate the move of a nurse from Oakland, California to Berkeley, California. And had the ZX been available backline in combination of NVIDIA Menelux Metro X2 range extender, the move could have been done much easier and sooner. The fourth key idea is that man-in-the-loop style data movement is becoming less and less important. Based on our observations, a lot of people still think data transfers as a simple end-user activities to be carried out using a GUI app or a CLI tool. Some even think that all data movers should handle this style of data movement. This is a misconception. In fact, problems in this category don't involve moving data at scale and speed, and often short distance too. So they have long been completely solvable with freeware on the server side, freeware and low-cost applications for end users. Here is a sample solution architecture for an organization to collaborate with external individuals. On the server side, I use the freely available Minio, which can be easily and quickly set up using, for example, Ansible. On my Linux notebook, I have this FileZilla Pro application tool. There's no need to pay for costly commercial solutions. Obviously, Zettar doesn't focus on this category. Next, I will introduce the concept third-party transfer. It's also a kind of a man-in-the-loop style data movement. A human operator issues instructions to data movers running remotely to move data between distinct storage services. Both data movement category 2 and category 3 have this style of a transfer as a subset. In passing, I will point out that the third-party transfer in category 2 can sometimes be transformed into a combination of a category 2 plus category 1 by applying the jokingly termed fundamental theorem of software engineering. The previously discussed biomedical instrument data collection solution architecture is a fine example. Many people in the research community still pay too much attention to category 2's third-party transfer. Know that such transfers are often carried out by users who are not IT professionals. Globus GridFTP and Fermilab's Big Data Express cater to such use cases, but neither is a good fit for the rapidly dominating category 1 involving fully automated transfers of massive amounts of machine-generated data. Next, I wish to show how ZX is used at a few customer sites. One of them is a Dell shop, so it runs Isilon NAS systems and the ECS S3 compatible object storage. Isilon comes with a single IQ software, but ZX simplicity, scalability, efficiency, and cost effectiveness soon became obvious to the customer. So a single ZX instance now is used for data exchange between Isilon NAS systems and the ECS. Let me show you how this works. Okay, browse 128, this, give it the name. You can see so far it's a single site, so local mode. So far there's nothing unusual. Target, yeah, this is the only difference. See, select, okay, we send it to, just double check, sure, it's okay. Save, give it a bucket, that's the only thing. Additional, but none. See, so far, because the ZX tight integration of different products, the usage are very much alike. There's not much difference, okay? So again, it's copying, and the picking up is pretty fast, but we don't want to wait right further. Let's just proceed. So now, the next one. At another customer site, uses our ZX to exchange data between Isilon NAS and the AWS S3. The previous demo should make clear the reason why they decided to do so. And here's another one. Some supercomputing centers still run tape operations. Modern tapes typically use so-called linear tape file systems, or LTFS. Companies like Quantum sells appliances which acts like NFS servers. ZX can connect to multiple such appliances to speed up data backup from a file system, for example. The fifth key idea is linear scalability. First of all, for an application to show linear scalability, the environment in which the application runs must be conducive. Otherwise, even applications designed with the linear scalability in mind, it won't show it if the environment is not right. In other words, the often quoted, just add more instances is not enough. In particular, for I/O-centric workload like moving data at a scale and speed, it is critical that the storage service must be set up so as to be linearly scalable first. That is, if it can provide a single node and attainable storage throughput TGPPS, then with n such nodes, the storage service should provide TGPPS in each node for a total n times TGPPS. Without linearly scalable storage, data moved along can never be linearly scalable. You cannot put a cart in front of a horse. Ideally, there should be more attainable storage throughput than the desired transfer rates to compensate for any overheads. Zettar strive to achieve linear scalability for ZX in 2016. Before SC16, we use a multi-setup described in this Intel ITP network block. A modest Dell C6320 2U4 node at each end, running memory to memory over the 5,000 mile ESNet loop, attained 200 GPPS. Each node contributed 2 times 25 GPPS equal 50 GPPS, but we didn't stop there. Memory to memory is not realistic. The litmus test is always storage to storage. That's what we did at the end of 2016 and January 2017. Back then, LCRS had 4 very modest data transfer nodes. So did NERSC, so we installed ZX on all 4 at each end, firing up 1 pair at a time. You see here, initially the transfer rate did increase progressively, then it tapered out. Upon investigation using field, a storage benchmark, we concluded that it was caused by limited attainable storage throughput from the raster file system. To confirm, we used the memory-to-memory transfer, compare IPER3's output versus ZX. The two were very close. But due to the use of a memory-to-memory again, the validation felt incomplete. So in 2018, Intel graciously landed 16 Optane SSDs. Back then, we had a testbed hosted at Slack. The testbed had 2 clusters. Each cluster has 2 storage nodes and 2 transfer nodes. We installed 4 Intel Optane SSDs in each storage server. With the help of their outstanding read and write performance, we were able to attain average 75 GPPS out of the hardware limited 80 GPPS. That's 94% bandwidth utilization. As a result, we were able to move 1 petabyte data in a shared storage with a full TLS encryption and unconditional checksumming over 5,000 miles in 29 hours. Our happy colleagues at the ESNet wrote the news about this. The above are side-to-side transfers. How about SSM and in a cloud? In 2020, working with the Weka.io, we showed that SSM linear scalability in AWS EC2 S3 environment with a 4 C4.AX large EC2 instances, 4 ZX SSM instances working collaboratively, pushed more than 3 gigabytes per second from EC2 to S3 from a Weka matrix parallel file system running EC2. Please see this video. Now let me briefly describe how we have made ZX simple, scalable, yet efficient. It has a peer-to-peer based design, so all nodes in a cluster know each other's state. Thus, the clustering is accomplished intrinsically by ZX, not with an orchestration application or a cluster workload manager like a Slum. As a result, high availability, auto load balancing, high efficiency, and a host other benefits result automatically simpler operation and management too. It is possible, for example, for any node to be a management entry point. Also, any node can join and leave. The new node immediately shares the workload, or the rest can pick up the slack. In passing, note that ZX is a genuine HPC-style data mover, so our cluster instances work collaboratively on the same data, which is usually stored in a storage that is either shared or replicated in real time. Let's take a look at the landscape of the data movers. This has been an ignored field for decades. Most established entries are long in the tooth. General availability, also known as GA, often indicates the time that the software's main architecture has been finalized. From then on, the architecture really gets changed. Thus, the older the GA, the less likely applications to leverage modern software engineering advancements. ZX evidently is the most modern one in the list. You may wonder how well ZX compare with other entries. Let me show you two examples. Zettar won at the grueling 2-month-long Supercomputing Asia 2019 Data Mover Challenge, and we beat all these entries. So far, we are still the only overall winner with the record unbroken. Here is the network topology used by the competition. All 100G links, the longest network latency is bigger than 400 milliseconds satellite level. By the way, the Data Mover Challenge exemplifies Category 3 third-party transfers. Since October 2020, ESNet has been rigorously evaluating various data movers, including a DOE-funded Invested 3, Globus Grid FTP, Fermilab's MDTM FTP, which is the basis of Fermilab's Big Data Express, and Zettar ZX. This is the latest Category 3 third-party transfer results between a pair of the Docker containers over ESNet's 100G SDN testbed, about 2,500 miles long. You may recall that in 2019, Zettar ZX beat out both Globus Grid FTP and Fermilab's Big Data Express at the Supercomputing Asia Data Mover Challenge. In 2021, ZX still beats out both. When a data mover cluster is used, if the storage throughput enables ZX linear scalability to kick in, the other two will be left far behind. Also, unlike these two, ZX doesn't exhibit the drop-like-a-stone symptom for large files. Finally, both are of the traditional client-server design, so cannot tackle, for example, file system replication easily. By the way, some may ask, how about async? I can aggregate many async instances and move around 100 terabytes per day. Sorry, sir. 100 terabytes equals 0.1 petabytes. These days, the migration between two high-performance file systems often involve tens or hundreds petabytes. Unless you don't care about migration efficiency and simplicity, 0.1 petabyte per day is not gonna cut it. I invite you to review this DOE Technical Report, when to use async, and for a definitive answer. And you have any questions, please ask. You're also invited to email me or visit the Zettar website's resources page. Finally, for an in-depth discussion for business, please coordinate with me offline. And then the story is still ongoing, and I would like to gratefully acknowledge Zettar's customers, partners, my Zettar colleagues, friends, and last but not the least, my family. Thank you.